And again, please remind me when I'm doing slides to hit that record button for the sake of anyone who's watching this. It's really weird to post this on YouTube and then look a few days later and see that maybe 30 people have watched it. And it's not all of you, but some people around the world are like having it come up and watching it. It's weird.
Where's the robots?
Yeah, with the robots.
Oh, do the robots watch lectures?
I'm pretty sure they have to. They watch everything, right?
Yeah.
I hadn't thought of that. Okay. I don't feel so good now.
The robots like you too, though.
All right, so angle tracking. We've got a process model, very common process model, first order autoregressive process model. Basically what this process model conveys is that the state changes slowly from one time to the next. My pointer changed. That's weird, I didn't change it. And then we have the measurement model. And the measurement model is actually what makes this one interesting because it's taking a sign, and if you're trying to estimate basically the inverse of a sign, there's an ambiguity. And that's what ends up creating the multimodal posterior because there's multiple angles that would produce exactly the same observation. And so the only way of knowing which angle is true, of being able to distinguish between them, is by the history, which again comes from our knowledge that the state can't change very rapidly over time. So it's a really cool example, I think. And hopefully all of you are getting a handle on the mechanics of doing optimal tracking and how that works. We're basically doing a numerical integration here and then just doing this calculation. And remember, the computation is proportional to the square of the number of bins that you're working with. And so, and we went through that. So all this should be review. And these are the things I chose. Go ahead.
Is that true in general, that the measurement function determines if the PDF has multiple modes?
No, nonlinearities in the process model can also create a multimodal posterior. It just so happens in this example that the process model is actually linear. In fact, it's almost stationary. There's a name for the type of stationary it is. It isn't quite stationary because when you initialize it, you don't initialize it with the same distribution as what it has in steady state, but after it gets through that initial transient, this becomes a stable process with finite variance, and it ends up asymptotically becoming a stationary linear process. So, I mean, in some respects, it's really boring. It's a scalar linear statistical process model. But this has the nonlinearity, but it could go the other way. You could have a linear measurement model and nasty nonlinearities in your dynamics in your process model. This example just doesn't have that. So I went through this. Some of these, I say I chose normally when you're not making something up, when you're working on an actual application. Instead, you need to justify these values usually based on understanding the process that you're trying to model, the process that you're trying to track. So you're talking about, for example, the variance of the process noise. This is basically the step size from one sample to the next. And you would have to say, well, I've studied the dynamics of my plant. If we keep talking about objects that are moving. If you're tracking a submarine, you can say, well, I know that for my sample interval from one time to the next, that the standard deviation of that difference is going to be no greater than X. And so I modeled that as though 2 standard deviations or 3 standard deviations times that number is what I said is my process noise, something like that. It's not I chose or I made up. It's more based on my understanding of what I'm trying to track. This is how I modeled it, and then this is how I later verified that those values are reasonable. Same thing with initial state. That comes from the domain knowledge that you have in your application. When you get down here, it's a little bit different because this is, now we're talking about the parameters that define the tracker itself. These first 2 big main bullets are really about the model design, but these last 3 are about the tracker design, some of the design decisions you make for tracking. And those are largely going to be based on, this is based on domain knowledge, but the number of regions and maybe the number of samples is probably based on what it is you're trying to do and how many clock cycles you're willing to throw at it. So the reasoning that you use as you go through and you're defending your design decisions are different when you're talking about the tracker design choices compared to the model design. to try to keep those straight. And these examples are a little bit off as we go through, because I'm really trying to illustrate the tracker, but I'm trying to give you hints and understanding a framework of how to design and how to justify your model design as well, which turns out to be the more important part. Okay.
What was the physical representation of alpha? A weighting factor
alpha,
of previous states? Or?
Yeah, alpha, you can think of it as a measure of how much memory it has, is one way of thinking about that. If alpha, and I'm sorry, I can't go back without screwing up the recording, but if alpha is 0, you've got a random walk process. So that basically means there's no correlation from the state at one time to the state at the next time. When alpha approaches 1, it starts to become a random walk process, and it's technically unstable. The variance then can grow with time. That's appropriate for some problems, but usually when your knowledge of dynamics are slow, you also have an idea of what the mean of your dynamics is, and you know they don't deviate too much from the mean. And so most people, most engineers, when they're working on this, set an alpha that's very close to 1, but a little bit less. I'll say a lot more about the model design a little bit later in the term, once we get through the initial trackers. Okay, and then we decided to represent is a pseudo-colored image, the posterior. This is, I'm working with synthetic data, so I synthesized it. And this is the sequence of measurements that were synthesized. And you can see this is the angle, and it changes slowly over time, just as I modeled it, just as I kind of intended it to. So when I synthesized the data, this is what it looked like. And then this was the key plot that came at the very end of the lecture, when probably many of you were exhausted and maybe mentally fatigued. And I was trying to make a lot of really important points that come up when you study this image. And for you non-robots that are here in person, I know the screen is a little bit washed out, and so it's a little bit hard to make out everything that's there, but on your computers you can always see the high-resolution images, or your smartphones or whatever. So I'd like to go through what sort of some of the main take-homes are of this plot. I know this is repeating what I said last Thursday, but it's important enough that I think it bears repeating. So the first thing is that this pink region down here is actually a transparent red region, and that represents basically minus infinity up to the 2.5th percentile of the distribution. And likewise, this upper pink region goes from positive infinity all the way down to the 97.5th percentile. And so if you look at the non-shaded region, the non-pink region, then that represents a 95% confidence interval. And I didn't shade the interval because I wanted you to be able to see it clearly. And so that's why I shaded the what was outside of that confidence region rather than what was in. So this is misleading because it's dark red, and it's really like, it should be white. Everything that's not white is outside the confidence interval. It's not that red is the confidence interval, but I think that's clear enough. I'll use that on a lot of the plots I show for examples that we're tracking. So if you get calibrated to this plot, you'll be good for the others. The vertical axis are the values that the state could take on. You can see I used a display range of -6 to 6 for showing what the posterior is, and I'm only plotting the first 200 samples. I could have gone on, but I didn't. The darkness of the grayscale indicates where the posterior probability is high and where it's low. So like a dark black region in here means that's a region where it's highly probable. And a white region is an area where it's very improbable. And so when you're looking at this, it gives you an idea of where the probable places are that the state can go and where the improbable places. The red trace with the dots, each dot is a sample, and I just connected them with straight line segments. And this is what the true state happened to be. The blue line is the mean of the posterior that I calculated directly from the posterior. The green is the mode, or the highest point. It's the maximum. And the yellow is the median. And so that's what all the features of the plot are. And in terms of the main take-homes from this, there's a lot. First of all, we had a very simple model, and yet it generated a multimodal posterior. And I want to emphasize again, when you talk to other engineers that have done state space tracking or taken classes on state space tracking, they're usually using an extended Kalman filter, a Kalman filter, maybe an unscented Kalman filter if they're fancy. And that would do horribly on this example because it's basically modeling the posterior so it's unimodal. This is a very simple univariate model, and it generated a multimodal posterior. And those techniques are poorly suited to a posterior like this. So be careful. You should have in your mind, whenever you're working on a tracking problem, is this possibly multimodal? And if so, then that can inform which type of tracking algorithms you'd want to consider using for it. In particular, would basically steer you towards particle filters. They're one of the very few practical choices when it comes to tracking a multimodal posterior. So this is very simple, and it ended up being multimodal. You can see the different modes over time. You can see the modes change slowly over time. That's because of that process model that said the dynamics change slowly. That basically the angle changes slowly. So we may not be able to tell at this time whether the angle is here, or even up here where it really is, or possibly down here, but it's only going to be one of those 4 places because we're getting measurements that are the output of a sine. The output of a sine could take on any of a multitude of angles, but based on our prior knowledge expressed by our process model, the state really could only be in one of those 4 places with 95% confidence. Another nice thing about this is the prior knowledge was that the state was close to 0 with very high confidence. So this started off with a very narrow distribution initially, meaning that at time 0 we had very high confidence in where the state is. In many of your applications it'll be exactly the opposite, where you may have very little information on where the state is and have a very high variance, in which case you'd see that there are modes all the way up and down, 0 and then every multiple of pi. You would see another one, and you'd see a lot of them, and then they would sort of come together pretty rapidly as time goes forward based on, again, our prior knowledge in that process model, because it's stable, and it's eventually the variance of the state is going to come down. We know that based on the process model alone. So whether this sort of starts out very, very far spread apart and then comes together, or starts out very, very tightly packed, and then sort of spreads out, as happens in this example, is all determined by how big you make that distribution at time 0. So that comes back to the prior at time 0 that you were asking about a minute earlier, about how that was entered into the code. In this case, we had very good knowledge, and so it's very tight. And so we see the posterior spreads with time. You can also see that it stabilizes, that after about 60 samples or so, you can kind of get that sense of that stationarity that I was telling you about, Andy, that the process model, even though we say it's very tight initially with a small variance, the variance grows. We have more uncertainty about the state as time goes forward, but that certainty is bounded because we had an alpha less than 1. It's a stable process model with bounded, stable variance asymptotically. And we can see that it's more or less reached that stationary state after about 60 steps. Because you can just, looking at the envelope, you can see it's no longer growing. There's no longer a growing variance of where the state can go. Another interesting thing about this is that I pointed out, and this was a really important idea conceptually, is that if you look at the true state, it's way up here. And one of the things I tried to mention last time is this tracker of the posterior is optimal. And even though the true state is out here sort of skirting the edge of the upper part of the 95% confidence interval, and sometimes being out of it, on average it should be out of it exactly 95% of the time. But you can see it's up here, but the tracker did not do the wrong thing. When you think mentally, we're doing, this is a course on statistical signal processing, and we've got an ensemble from which we're drawing samples. We could have had exactly the same measurements, but different possibilities of where the state was and how the state unfolded over time. And what happened here was improbable for the first 40 or 50 samples. That was, you could almost think of that as unlucky, because the evidence was that the state was probably going to be here or here, based on the posterior. If you could repeat this experiment where you happened to get exactly the same measurements, but you had different states many, many different times, Based on, we could calculate what the probabilities are, but most of the time the state would be in one of these two modes that are the tallest and have the most area. It was improbable that this happened based on the measurements we have, but the tracker didn't screw up just because all the estimates of the state were far away from where the state really was. There's no tracker that would perform well on average, across the ensemble, whereby it would estimate the state as being up here where the true state happened to be. And that may be difficult because as engineers, you're often thinking about, well, if my tracker is working well, the estimated state should be close to the true state. That's not true. It's true on average, but it's not true for a single realization. This is a single realization that we're looking at. So if you could repeat this experiment many, many, many different times, and your figure of merit was mean squared error, what's going to be best is the blue. The blue would be better, even though it's in an improbable place. It looks kind of dumb because it's not tracking the modes at all. If you're trying to minimize mean squared error, we know the mean minimizes the mean squared error, the posterior mean squared error in the Bayesian sense. And so it's far off in this case. But if you could repeat this experiment again and again and again, this blue line is going to minimize the mean squared error. It's optimal in that sense.
When you repeat the experiment again, you'll get a different set of observations. So the blue line will change.
Yeah, that's true. But you can imagine repeating the experiment enough times that you happen to find one where you get another set of measurements that are identical.
Yeah.
And you could do that again. And the main point that I'm really trying to get across in this long-winded spiel is that you shouldn't be paying attention to whether the estimate is close to the true state. That's misleading. For a particular realization, it may be way off, especially in an example like this where it's multimodal and the true state may be off in a different mode than one of the other modes that you're following. So you should be thinking, is it performing well on average? If you really wanted to know whether you had a good tracker and you were able to synthesize data, you'd want to synthesize more than one run. We're only looking at a single run. Realization is the term I use, but you could call it a run. So if you repeated the experiment many, many, many different times and then calculated how did it perform on average, then you'd have an idea of how it performed across the ensemble rather than for a single realization.
Could you use a likelihood function to say that, like, given that I know that the y was this at this time, this is the probability density function of x, and therefore draw samples from that distribution to get more values from the same ensemble?
Oh gosh, I don't know. I honestly, I didn't even quite follow that. I don't know. It's unimportant that the measurements are the same, but the reason I talked about the case where the measurements are the same is just to drive home the fact that it missed the state here doesn't mean that it performs bad across the ensemble. The measurements really wouldn't have to be the same. For that to be true. You can do it again, you get a different set of measurements, and maybe it happens to track well that time. You should think about the ensemble. You're graduate students in electrical and computer engineering, most of you are near graduation, and you should be thinking about the performance across the ensemble. Even though you're often working with data, we've got a single realization, you've got a single set of measurements. But especially when you're synthesizing data, and checking the performance of the tracker on synthetic data, then you can have as many realizations as you've got time for. And it's just clock cycles.
And when the drone blows up the civilian place instead of the other one, you're just like, well, it was a realization.
Well, I don't know if I claim that their processes are optimal.
Yeah. I think I'm not going to touch that one.
The 95% confidence, is that something that you could increase?
When you say increase, I'm not sure quite what you mean. Do you mean, could you get a 99% confidence interval?
Yeah.
Yeah, anything you want. I mean, name it and you can compute it. You've got in this case, we've got the posterior PDF, and so you can calculate any percentile you want. Once you've got the PDF, you can kind of do anything. Trick is getting the posterior, but yeah, I mean, 95% is just kind of a common choice, but you can pick anything you want based on your application. You certainly have a wider confidence interval. Another point was, we've got the mean here. The mean is what a lot of the extended Kalman filter and extended Kalman filter, the Kalman filter, they all estimate the mean of the state. And the mean is optimal in the sense that it minimizes mean squared error. But in this case, you can see the mean is often in an improbable location. Well, actually, there's often a mode there, but there are at least times where the mean is at a point that is very improbable. And you should be mindful of that, because very few engineers will go through the trouble of trying to visualize what their posterior looks like. Most will just say, oh, throw a Kalman filter at it and we're good. Or, you know, one of the variations of the Kalman filter. But you can see here that depending on what your application is, you may be unhappy with that. You may not want estimates that are improbable, which this does in that case. You can see the median does much better. The median and the mode are pretty close to one another. Again, the median is basically the point where half of the area is on one side, half the area is on the other side. And usually that dividing point happens in a mode. And so the median is almost always in a mode, and that makes it kind of a nice choice. And the mode, of course, is the highest point. One thing that isn't illustrated by this example that is a little bit hazardous about a mode is that although this mode is highest right here, it could have changed in a sample where the mode was suddenly highest up here. So one of the things that can happen when you're tracking a mode is that you may be tracking, and then suddenly it jumps up here, and then it jumps back down here. It switches basically from one mode to another. I don't see any examples where that actually occurred in this particular example, but we'll see some in subsequent examples that I'll show you later. So that's one of the things that could have happened.
So if we increase the number of states in our state space model to add like some more memory of like a velocity that the state's changing with, could we like prevent it from like jumping back and forth that way?
No, if what you care about, so this is getting ahead a little bit, but conceptually there's two different things that you may aim for. What most people try to do is get the best estimate of the state given the evidence that they've had so far. And if that's what you're trying to do, if you say, tell me what your best estimate of the state is at time 40, and I don't care if it jumps around to something completely different at time 41, just tell me what the best is at that time. Most of the trackers are trying to give you that. And so most of the trackers could have a big jump. If you suddenly get evidence, especially if you've got one that's multimodal, and suddenly you've got the evidence changes and you get a measurement that tells you your state is way up here, then there may be a big jump in your estimated state that's inconsistent with your dynamics. It's possible. But there is a set of, not very many for our domain, but another thing you might aim for is what's the most probable trajectory. So in that case, you're looking for the entire sequence of states through the entire thing. And a sequence it's improbable that an entire sequence would have a big jump in it, because that would be inconsistent with your dynamics. And that gets more to the hidden Markov models that Eric was asking about a lecture or two ago. I'll talk more about that later, but there are different things you can ask for depending on what your application is, depending on what you're trying to estimate. So in your mind, you may think, maybe I'm trying to estimate the entire trajectory. Maybe I just care about the best estimate of the state at this particular time and not about continuity of those estimates.
And this includes, because it's the posterior, it already includes the process model and that prior knowledge that we have. So any
Correct.
sort of knowledge that says it can only change between modes so quickly or whatever is already included in this result.
That's right. That's already here. And if we had a white noise model, white noise process model, then you would just see horizontal stripes that were at the mode. Well, they would still change, but they would be at the modes that were consistent with the measurement. But the measurement would change randomly from one time to the next, and so the modes would jump from one sample to the next, and they'd be completely uncorrelated. So yeah, I mean, the process model is why we can see, some of these modes seem to follow kind of a smooth trajectory. It's because the process model has that prior knowledge that the state can't change quickly over time. So yeah, you're exactly right about that. There's really a lot in this one plot. I mean, 17 minutes on one slide so far, in addition to what we did last time. Do you guys have any other questions on this? There's a lot there, I know. Okay. Well, this is just zooming in, and honestly, I forgot why I zoomed in. There is a mode we can see down here that it's going off into a zone where it's becoming less and less probable. It's possible the state is down there, but this is inconsistent with that process model. And this goes back to the difference between having an alpha of 1 and an alpha that's slightly less than 1. This wouldn't get any lighter really if alpha had been equal to 1, because that would be a random walk model, and this wouldn't be more and more improbable as it took on more and more negative values. But I made it stable, it had finite variance, and I basically told it that some of the prior knowledge is that the state has an average value of 0, and it doesn't go too far from 0. And that's why this mode gets lighter as we move forward. And again, you can see the prior distribution taking into account just one measurement. It's really tight right there, so you can see how it spreads also. But I don't really have a lot more to add beyond that. Okay. All right, so one of the things I've asked you to do for the homework is you saw in this example how the state dynamics, by state dynamics I'm basically just talking about the process model, how we're expressing our knowledge of the prior dynamics in the process model, and having that helps reduce uncertainty. That's why we had tighter modes and a smaller number of them. One of the things that would be a good exercise for those of you that haven't started on homework 2 quite yet is to ask yourselves in your own mind, what would happen if this process noise increased or decreased? And I've asked you to try that and see, but you should think it through beforehand. If you increase this, what's going to happen? If you decrease this, what's going to happen? And similarly on your measurement model, is you increase the power of that noise, the variance of that noise, or decrease it, you should think, how is that going to change how the posterior looks? And I hope we have people who did the homework correctly present on Tuesday, so we can see how that works in the models that they've come up with. So I'm not actually going to answer this question, but we'll circle back to that on Thursday. I'm just asking you to consider it and think about it. So I've got one more example for you, and this is the linear case. So the process model is the same. The only thing is now our measurement model is that it's a constant times the state. So the measurement is kind of the state in this case, but it's noisy. We've got some measurement noise there, so we can't simply estimate this. Well, we could, but it wouldn't be as accurate to estimate the state as being 5 times yn. I mean, that would be essentially a maximum likelihood estimate. We could do that, but we can do better by incorporating this prior knowledge. So this is just another tracking example, but in this case it's linear. That's the difference. Both the process model and the measurement model are both linear.
Is the denominator in the filter step, is that the same as the denominator in the Bayes' rule that we saw kind of on the first day?
It's equivalent, yeah.
Okay.
It's equivalent. A good way of thinking about this is it is the integral of the numerator.
Right.
And so if you were to integrate this whole thing, it's the numerator divided by the same thing, but it becomes a constant when you integrate it, so that guarantees that the posterior has an area of 1. So the way most people think about this is it's kind of just a constant. It's not a function of the state, and it's kind of a nuisance scaling factor that you have to deal with, but it's not really problematic because really what we're trying to do is estimate the state, and if you've got this constant that is not a function of the state, then it's not going to have a big impact.
Is it common to skip the integration and just kind of periodically just divide by some number just to keep your posterior from blowing up?
Yeah, actually we'll see how that's done exactly today with particle filters.
Oh, okay.
Yeah, that's what they do essentially. There's a normalization that's done usually at each time step to make sure that the area of that estimated probability is 1. Turns out to be really, really easy to do, and so this doesn't turn out to be troubling at all. So it's coming. Okay, and again, you can't get away with this typically when you're presenting a model design because you can't You can't just make up values. If I say, you're presenting your homework or your project at the end of the term, and I say, so with your process noise, you've got a standard deviation of 0.4. Where'd that come from? You can't say, well, I just chose it. It's not acceptable. Like there needs to be a sound basis for all of your design decisions. You need to be prepared to defend them. But since I'm the instructor and I'm just creating examples to apply these tracking algorithms, I can get away with that. But it's a bad example for you. Do as I say, not as I do, kind of thing. So here's what the data looks like. The state looks very similar. In fact, it looks maybe identical. I don't remember exactly what it looked like, but I may have seeded the random number generator the same. Of course, the measurements are going to be quite different now because there's no nonlinearity. So that's different. But the state may have turned out to be, oh, I have it right here. So I did seed it the same. So this is really just with a different measurement model. And here is what the posterior looks like. And this is what most people have in mind when they're working on a tracking problem. They think the distribution may be really tight initially, it may be very broad, but eventually it's become this unimodal thing. And really, if I know the mean of that distribution and the variance of that distribution, then I'm pretty well set. There isn't really much more to be said. And they're quite happy with that. And in this case, they would be right. It is unimodal. It turns out everything is Gaussian, including the posterior. At any given time step, if we were to look at the distribution, it would be perfectly Gaussian in this case. It has to be, it's a linear model driven by linear Gaussian process noise and Gaussian measurement noise. Another kind of cute thing that happens is the mode, the mean, and the median. You look at this and you're like, you forgot to plot two of them. But I didn't. It's that the median is on top of the mean, which is on top of the mode, and they're all exactly the same because it's a symmetric distribution with its maximum value at the point of symmetry. So they end up being the same. You can actually see MATLAB kind of struggling to know the order of the plotting if you look really closely at a few points where there's a little speck of green that comes through, but they're all in exactly the same place theoretically. You can again see that the true state is not always close to where the optimal estimate of the state is. And again, I'm trying to emphasize that this does not convey a problem. The fact that the state is way down here when our estimate is up here, our estimate did not screw up. This is optimal. You can't beat this. There's no beating this. Like if you decide what your criteria is, if it's mean squared error, you can't beat the yellow line, which is right on top of the blue line. Like you're not going to beat it. It's impossible across the ensemble. But we're looking at a single realization. And for a single realization, state may be different than where your optimal estimate is.
So the prediction here seems to lag the true values. Is that a coincidence?
Yes.
Okay.
No. That's an excellent question. So what we're talking about so far are causal estimates of the state, and being causal, you would expect it to lag where the true state is. The true state heads down here, and the causal estimate comes down a little bit later. Not a coincidence. It will happen consistently. So maybe earlier when I was plotting at the difference here and saying that wasn't a problem, I'd been ignoring the fact that it's a causal estimator, and that it often will be a little bit late in detecting when the state goes down or when the state goes up.
Because the state's actually changing faster than the process model would predict, that sort of thing?
No.
You need the
It's
measurements.
it's
to
not-
Because the
update
optimal
where it's
causal
at.
filter is not the same as the optimal acausal filter.
Right.
That's it.
Right.
It's not using any information from the future. Eventually, if we have time this term, we'll talk about smoothing. Smoothing uses the past and the future. And when you're using the future, all that delay goes away. Then you have no lag at all. But in this case, we're getting the best estimate of the state, given all the measurements so far, and given our knowledge of the process dynamics. But it's only the current and past measurements that we have with which to estimate the state. And it does take some time for it to respond when the state goes down, for that evidence to accumulate and for the optimal state to really be lower. So the lag is not a coincidence. It's a consequence of using a causal estimator. That's a great question. Something I had overlooked. But the main point of this example is that if it's linear, you can do a common filter. Working with one mode is perfectly fine. And there's plenty of applications for which you're only dealing with one mode. Your posterior is unimodal, and in that case, if you know the mean and the standard deviation, you're great. You don't really need to track the entire posterior. You know, I've got 400 bends. I'm representing the posterior with 400 distinct numbers. And really, in this case, I could have done it with 2. The mean and standard deviation are ample. And that's all the common filter tracks, is the mean and the standard deviation of the posterior. And in this case, that turns out to be optimal. In fact, you couldn't beat it. The common filter would generate an estimate of the state that is identical to these 3. It would be no different. That's what the common filter will give you. So, so whether you need a particle filter or whether a common filter is sufficient for your application, you need to do some digging as good engineers. You need to spend some time and try to figure out whether you're dealing with a posterior that is multimodal or whether it's unimodal. If it's unimodal, you're probably perfectly fine working with a common filter or one of its variants. Yeah? Okay, that was the main reason that I did the linear example. We'll come back to that when we do the common filter, and this is just a repeat of the zooming in and seeing the true state's different. The uncertainty is growing a little bit with time. It's Gaussian.
If we can show that the likelihood function is unimodal and that the prior function, where you're just looking at the change from one state to the next, are both unimodal, can you also say that the whole thing is unimodal?
I'd have to think that through. I'm not sure. Because you're looking kind of at the product of the two. And it's complicated because you've got the dynamics. You've got the prior posterior as well. It's not as simple as the case where we don't have dynamics. Like when we first started talking about Bayesian estimation, you're like, well, it's just the prior and the posterior. I'm in a one-dimensional space, I can multiply them together. But when you make it multidimensional, and your prior knowledge is not about where the state is, but it's about how rapidly the state changes, that makes things all more complicated. So I don't know if that rule is true or not. It may be. I'd have to spend probably a lot of time thinking that through to answer that question. Oh, you know, one thing that is surprising about these examples, or maybe surprising that I maybe didn't emphasize enough, is usually when you get more measurements, you can estimate the state more accurately, right? I mean, usually start off where you're like, I don't know where the state is. And as time goes on, you're getting evidence. These measurements that you're acquiring give you evidence about where the state is. So you get more and more certainty about where the state is. Both of these examples were sort of counterexamples to that, where you had more uncertainty about the state as time went forward. At time 0, it was very tight. We knew where the state was, more or less. But as time went on in this case, it got worse. And the only reason for that is that in both these examples, our knowledge of the initial state expressed by the basically the variance of the initial state PDF was very tight. So in both these examples, we're starting things off and we knew where things were. It's too bad Aaron isn't here today because he's keen on using IMUs to track where a rocket is. And a rocket is a good example of, at time 0, you know where it is. You know, you've got great knowledge of the state. As time goes on, you're going to have more and more uncertainty. But in most applications, you start off not knowing. And you usually initialize the state, so you've got very wide variance, and then it narrows in. It gets the PDF, the posterior gets tighter with time rather than looser. And again, mean and covariance, it was a single variable, so it even would have been just mean and variance would have been enough in this case. And the common filter would have been optimal for that particular example. So, see, that finally brings us to the end of the optimal tracking topic. This is very exciting. It's really cool because it's optimal and you can't beat it. Like none of the tracking algorithms I'm going to show you for the rest of the term are as good as this. In the sense of accuracy, like this is the best, and all you have to do is spin clock cycles, and you can get exactly the posterior PDF, and from that you can do anything you want. It's sort of sad that this is overlooked so much in a lot of the literature and the textbooks in state space tracking, but it's like you can actually compute it pretty easily as long as you're in low dimensions. Both examples we went through were one-dimensional examples. You could probably do it in 2 dimensions. Although then instead of n squared, it would be like n to the fourth in terms of the bin width or the number of bins you're working with. So that makes it, as soon as you get past 2, you're probably spent, you're probably done. And which means you obviously can't go to high dimensional spaces, which is where most engineering applications are. So that's where this whole thing breaks down. Colin?
What if you had like a parallel processing scheme and you dedicated one processor to each state and somehow
if you wanted to do that, it could. This could be done with parallel processing. But when you think about how many processors you need, if you've got, let's say you're doing 100 bins, one-dimensional example, and for each bin you could do the sum across all the other bins, and so you'd need 100 processors. And each processor, could crank on that. But if you go to 2 dimensions, now you've got 100 squared bins if you're going to use the same bin width. So now you went from needing 100 processors to needing 10,000 processors. And you can imagine where things are going to go if you try to go to 3 dimensions. So it doesn't help. They can't make enough processors to keep up with how bad this gets, how quickly for practical engineering applications. There are other numerical integration techniques besides the simple ones that we talked about, and you might try some of those, but fundamentally integration is really hard in high dimensions, and that's why people don't do it. The fast techniques also don't scale well with high dimensions, so you're kind of in a corner here. It works beautifully in 1 dimension, but you go much higher than that, you're just done. But it does provide a lot of insight, and part of the reason I'm going to use this is I wanted you to know what it was, because we'll compare everything to it in low dimensions with the idea that what these techniques do and don't do in low dimensions, they probably have the same behavior and worse in higher dimensions. So if you see weakness in 1 dimension, it's certainly going to be there in higher dimensions. And there's other problems that will come up in high dimensions as well. So it's a nice basis of comparison. It's a gold standard with which we can compare for low-dimensional, simple tracking problems. So I think that's it. Any last questions before I end the recording?
So you mentioned how in many cases the estimate gets better with as we have more number of samples.
Because you get more measurements.
More measurements, right? Yeah. Along the same lines, if we make measurements faster, so we have more samples in the same amount of time, we'll have better estimate. But maybe that's the same as having low variance in the measurement model, in the system model.
Yeah, very good. I'm not sure everyone quite followed what you just said, but yeah, you're right. So you're like, well, look, I know about this cool thing called the sampling theorem, and the sampling theorem is normally used in such a way that you could say, I can, as long as I'm satisfying the Nyquist criterion, then I can get away with just having 2 samples for the highest frequency. That's all I need, which is an amazing result, but we all know it. But you're talking about going the other way and really oversampling. Like, well, I can take something that's sampled at whatever rate, and I can upsample it, and I'm not changing anything, so why not upsample it? Then you've got more measurements, and more measurements should mean that we can track better. There's 2 things that break down when you do that. Good question. So one of the things is that we have x of n plus 1 is equal to, in our examples, alpha x of n plus the noise. And if you're really talking about sampling something from a continuous time processor, if you're going to upsample it, then the variance of this noise basically represents how much x of n plus 1 deviates from alpha times x of n as you go from n to n plus 1. And if you make that period of time shorter, then you're going to decrease the variance of your process noise. If you're decreasing this noise, then you're putting more weights on your process model. So you sort of attempted to get more information by essentially putting more weight on your measurements by having more of them in a period of time. But this counteracts that effect because you're going to have to decrease this noise, and that will exactly zero out or cancel exactly what you were trying to do by having more measurements. So you won't win because as you turn up the sample rate, you turn down the variance on the process noise. And I'll go over how to do that exactly a little bit later in the term. So that's one thing. The other
Can you
thing...
just make your one sample that you decide to go for in that time step be the average of multiple measurements?
You can, but when you upsample, you're not really gaining anything. You're basically averaging anyway when you upsample a signal. I don't think maybe I didn't quite catch your question, but I don't think averaging multiple measurements were from an interpolated signal. You're just getting back almost to what your original measurement was. But there's another thing that we would violate if we did what Amit suggested. That is also important. Generally, this is some nonlinear thing of the state and our measurement noise. And one of the things that I tried to emphasize earlier, at least I stated earlier, is that when we look at the expected value of, this is generally a vector, and so you usually look at the outer product. So to get the outer product, I would do V of n plus L transpose, assuming it's real valued. All this could be generalized to the complex case, but I'm not going to do that because we usually don't need it. And then this was delta of n plus L times some covariance matrix R at time n. And the key thing I want to emphasize here is the delta n plus L. This is a Kronecker delta, and basically says that if you look at the correlation, I'm assuming it's zero mean here, so if you look at the correlation of your measurement noise between one time sample and another time sample, it needs to be uncorrelated. If you upsample, you're introducing correlation in your measurement noise, and you're breaking one of the fundamental assumptions of the model. So don't do that, for both reasons. It's also going to use more computation with really no performance gain, so you don't win in doing that.
So
Don't do it.
So in the real world, a lot of the time, it's nice to work with discrete time systems. A lot of the time, we model things classically with continuous time systems and then convert to discrete time. So in this case, we're basically using Euler's method to approximate the differential equations. Or, I mean, a lot of the time, you end up using Euler's function to approximate the differential equation. You don't have to do it that way, but just...
Yeah, and there are better ways. If fundamentally the model that you're starting with is not in discrete time, but it's in continuous time, then you probably know better than I do the various ways of converting those state space models and representing them as discrete time processes. There's a number of ways of doing that.
I guess I was just trying to comment that a lot of the times that process noise or that measurement noise is two parts of it. Is one of it is it's like there's some real process noise that's underlying because you don't understand the process, and then part of it is from the time sampling. So
That's true.
if you
That's
don't
true.
upsample the data, but you increase the data rate that you're actually getting real samples, you can decrease the variance sometimes because part of it is just due to that uncertainty in your approximation of the continuous time system. So
That's
you
a
might
great
get
point.
some wins there, but then at some point you're going to run into stuff like thermal noise and
Yeah.
things that really are white noise.
Thank you for saying that. You're exactly right. This, to the extent that this is an approximation of a continuous time integral or derivative, depending on how you look at it, it's not a very good approximation, and a higher sample rate makes it better. Yeah, that's a good point. But if some of the error in that approximation of the derivative or the integral can also be sort of lumped in to the process noise. So you can kind of account for it that way. But I'm just repeating what you said. But you're exactly right. Yeah. One of the fun but difficult things in teaching students that are so far through the program and are so capable is you're asking questions that are far ahead of where I've gotten so far. So I know some of you aren't following all these discussions that we're having and the cool questions that are being asked. So just bear with me. We'll get to a lot of this. It's coming. Anything else on this topic? All right.